Dear friends, hearty welcome to the online problem solving session organized by Maths Aspirants groups. As you know, Maths Aspirants is a collective of mathematics students, research scholars, and faculty members initiated by myself in 2017. And after the COVID, we used to organize online problem solving sessions and online test series. As a part of the online problem solving session series, today we have a session on basics of linear algebra. We're blessed to have Dr. Sayak Sengupta to handle the session. Dr. Sayak currently completed PhD from Binghamton University, USA. He did his MSc from University of Calcutta. I would like to express my gratitude to Dr. Sayak for accepting our invitation and joining with us. I'm sure that today's session will be really helpful to all those who are seriously preparing for different competitive examinations. I welcome everyone to this program. Welcome, Sayak.
Yeah. Thank you. I would like to begin by thanking Dr. Vinod for asking me to lead this seminar or problem solving session, whatever you call it. As Dr. Vinod said, that I graduated this year from Binghamton, and my advisor, although he's not a number theorist, but he has published a lot of papers in number theory or related areas, and he is very much interested in geometrical aspects of number theory rather than the algebraic aspects. But we can talk about it if you have any questions later. So I don't want to take up any more time introducing myself and my ideas and research. So I will take it for granted that we have mixed people in here. Some people are doing their BSc degrees, some people probably in their masters. So I would like to begin with the basic definitions that every book provides and slowly build our way up to some more or less advanced topics. Of course, this is just a single lecture, so I won't be able to cover things where complex analysis or other kind of stuffs are involved. Especially, I will try to avoid all the analysis stuffs. So that kind of ensues that more or less I'll be talking about vector spaces over R or vector spaces over Q. And during this session, if you have questions, please feel free to interrupt me. And I encourage you to ask as many questions as you. So as I mentioned, so let's start with the very basic. What is a vector space? So the name, in fact, came from the vectors as we know it. Mostly it's written in terms of columns, but sometimes people also write it as rows, like a matrix. You can think of this as a matrix with a single row or matrix with a single column. That's how the name came. And after that, it was generalized later. Not sure the exact date, but it was definitely a concept which was later developed into something that we are seeing today. Okay, so vector space is basically you have a group V. I'm using the letter V because of the name vector. And you will also have a field F. And then basically all the operations that a field does, the F will have that, and all the operations that V does, it will have that. And for good reason, we want some interaction to happen between V and F. So the interaction is, we can also think of this as group actions, but if you have not seen group actions, so you don't have to think about it. It's just some kind of operation that tells you how F and elements of F and elements of V mingles with each other. For example, you will have C. So when these two things comes into play, we will write it by this. So this is an element of the cross product of F cross V, C being an element of F, and small v being an element of big V. And I will send it to something that is this, where the dot depends on how you define the dot. So in this case, for an example, I mean, you can think of the field F to be R and V to be maybe some Cartesian product of R with itself. And then C dot V is just you're multiplying all the coordinates of R to the n, for example, with C. And that's how we define the dot in this particular example. But you can create more examples where dot is defined a bit differently. And once we have convinced ourselves that for this particular vector space and this particular field, whatever dot means is fixed throughout the problem or throughout the research problem that you're dealing with, then we will just stick to writing CV instead of writing C dot V all the time. Okay, so just for the definition, I'm going to keep writing C dot V, just for the beginning, I mean, and then after that, we'll move on to CV instead of C dot V. So as I was saying, the mingling part, C dot X plus Y is going to distribute very nicely, exactly the way we want it to. And the same goes for summing up the scalars and then doing the dot with some vector X. That also distributes properly. And also you have the one element, which is the multiplicative identity of the field F. And if you multiply that, multiply meaning this dot thing that I am talking about, with some vector, any arbitrary vector X, then it will give you back the vector X. Okay. So you don't really, if you, of course, haven't studied field theory or anything, you don't really need to know a lot about the field itself. It's just about, you can make sense of all of the things that I'm saying if you just consider F to be a Q or R. Everything will make sense. Okay, so there is no need to have some specific knowledge about fields. Of course, these fields can be made to be as arbitrary as possible, and you can get different kind of structures out of it, but that's a different kind of study, which is generally not something that people in linear algebra study, or students in linear algebra study. It moves on to a different field. So we are going to restrict our attention to R and Q mostly. So that's why we are not really interested in studying this field itself. And of course, you can talk about subsets of this group V that we're considering. So if this subset happens to be a group itself, and in its own right, it happens to be a vector space, then we will call W a vector subspace of V, or sometimes linear subspace of V. Now, there are some properties which are kind of a consequence of the definition, but it is not it's easy to derive it, but it's not trivial. You have to work a little bit in order to derive it, but it's not hard. Okay. In other words, so what I mean to say here is just these three things which will be used throughout the session. So if you multiply some vector with the zero element of the field, then you will get the zero vector. So this zero is the zero element of the field F, and this is the identity of the vector space V, which we will denote by 0. Okay, and same goes here. -1 F, which is just a negative version of the multiplicative identity of the vector space of the field F, times X is going to give you minus of X. Well, of course, minus X makes sense because X is there in the vector space. If X is there, then minus X is also there. Where, of course, by minus X, we mean the inverse of the element X. And the same goes for C dot 0, you get back the vector 0. Okay, so as I was saying, from this point onwards, I'm going to write Cx instead of writing C dot X.
Whatever we multiple with 0, we get 0 as a vector. Am I correct?
Yes. So you're talking about the first point, right?
Yes, sir.
Yes, that's right. That's right. So you take the 0 element of the field and you multiply any vector to it from the left. Actually, this is a left multiplication, so you have to be careful about that. So and you do that, then you are definitely guaranteed to get the vector, the 0 vector.
0. Same as the third point. 0 is
Third
the
point
vector,
is,
C is the
yes.
field. In right side, we get
That's
0
right.
is a vector.
Yes, so this is also the 0 vector, and this is also the 0 vector. Yes.
Okay, sir. Thank you, sir. Thank you.
Sir, how to prove remark point, please?
Sorry, can you repeat that?
How to prove remark point first?
The first
Tell.
one is 0 times x is 0.
Yes, sir. Yes.
Well, this is a standard proof actually. You can you can use any book that you want. I'm sure there are a lot of linear algebra books that you have at home or someplace in the library, but it's a standard proof. This is not a research problem. This has been known. So pick up any book that you want and you look at the basic examples. For example, the book that I'm using is a book by Gilbert Strang. You can definitely find it there. Or you can pick up the book from, I think there's an Indian author book that I have, which I really like, which glorifies the geometric properties of the vector fields and how it can be applied to surfaces and cubics. I mean the theory. There's also vivid proof of that. Okay, so you can in fact, go ahead.
Sir, ये vector space relating, sir, ये जो teach vector space relating to group theory.
Vector itself, the set of vectors itself is a group, but I'm not really going towards the group theory part. It's just that it has some group structure, which I'm writing additively. And you have a field, and they have some interaction with each other using this properties right here. That's all I'm saying. What group structure you have, it depends on what you're working with, but we are not, the linear algebra part at least, it doesn't really concern too much with the group structure or the field structure itself. Of course, you can move to some other topics which relates to linear algebra, but yeah, that's a different thing.
Okay, thank you.
Does that answer your question?
Thank you.
Okay. Okay, so yeah, we have described the definition and some properties, basic properties of vector space. Let us look at some examples. Suppose you have some non-empty set X, and we are considering all the functions that you can define on X, and the codomain is R. So basically all the functions that goes from X to R. Okay, if you consider something like this, then this can act as our vector set of vectors V, because you can define the operation between the elements of this set as the normal plus. So you can define the pointwise addition. Say F and G are two elements of the set, then you can define the pointwise addition as Fx plus Gx, where of course X is an element of the big X. And that clearly is a group. And if you pick up an element from R, whatever it may be, say you pick up an element small r from big R being the set of real numbers, and you multiply that with f. How you define it is also pointwise scalar multiplication. So you define it like r times f. So basically, I should write the dot here. That just means r times fx, which of course makes sense because this guy is in the set of real numbers. And on the right-hand side, you get two real numbers, and the multiplication is the obvious multiplication between two real numbers. So this way, this becomes a vector space. And vector space over R, of course. And the same thing can be made sense over Q or any field really. I mean, it doesn't really matter what you're picking, but as I said, we will restrict our attention to either Q or R so that you don't have to think about arbitrary fields. Now, the second example would be a subset, or I should say a subspace of example 1. So F naught XR is really, it's a subset of FXR, script F XR, but we are not considering all the functions. We are considering exactly those functions such that the set of all the x's where F does not vanish is finite. So these kind of sets are called support of a function F. Okay, so you are considering, yeah.
Sir, in second one, what is the identity value, sir?
Identity of?
Second question.
Yes, identity of what?
Vector space, sir.
Okay, so you can think of this as, let me think. So you can think, you can just take the zero function. Okay, you can take the zero function. So you are sending all the elements of big X to the zero. You want, and that means that this function is never not zero. So that means that this set it satisfies this particular condition that this is finite. The support is finite. So it's just the function. Let's say, what do I want to call it? Let's call it I of x is 0 for all x in X. Okay.
Sir, here identity element is f of x equal to 1.
F of x equals to 1. No. It's just this element. So the identity function must be a function, right? The
Sir,
identity.
this is identity function for addition. I'm asking identity function for multiplicative, sir.
Oh, multiplicative. So this is not a multiplicative group because, as I said, it's defined in terms of plus. So there is no multiplicative operation in this group.
So vector space means both the signs will include, no, sir? Plus and dot.
The vector space for the vector, the set of vectors itself, only the plus sign is being used, and for the field, you have two binary operations: the plus and the multiplication. Okay, so
sir. Here want to satisfy. Here condition should satisfy 1 dot vector equal to vector should come, no, sir?
Sayak,
yes.
Let me interrupt something to say something.
Sir?
Yeah, Ramesh.
Yes, sir.
Yes, Sayak, let me tell something in between. see, Ramesh, the dot operation in vector space is a scalar multiplication. So there is no, we are not looking for the identity for multiplication. Okay. So
Okay,
only
sir.
that property 1 into a vector will be equal to that vector.
Yes, sir.
Okay. So I request all the participants to reserve the questions to the end. Otherwise, we cannot go to the problem section. That's why.
Okay, sir. Okay, sir. Okay, thank you. Thank you.
Yeah,
Okay, sir.
Sayak, you can move it.
Okay, all right. Right, so this is how you have, this is basically an example of a subspace of example 1. And now you can make new linear spaces out of the ones that you already have by this particular idea that if you have two vector spaces V and W, which are defined over the same field F, and we also assume that W is a vector subspace of V, then we can define an equivalence relation where the equivalence relation on the set of cosets, because this is a group, the set of cosets actually makes sense. And this is how we define cosets. Okay, so this will be a group naturally. And this will also be a vector space with the kind of similar idea. Okay, so this is, you are making a new vector space out of two old ones, provided that one is a subspace of the other. This is called a quotient space, which is kind of a natural name because it is also called a quotient group by its own right. Okay, and I've described how you can define the equivalence classes as this. So the dot product is going to be the same as C dot. So C dot V plus W is going to be C dot V plus W and so on. So the things are going to make sense, and you are going to use all the properties of quotient groups and things like that in order to make sense of the definition, the properties of the definition that it must follow in order for this to become a vector space. Now we have the first three describes examples of vector space. So let me give you a non-example. So something that is not a vector space. So pick one of your favorite number, n. When I say favorite number, I want to pick a positive integer. Okay, so pick a favorite positive integer n, and then define this set Vn to be the set of all polynomials over some field f. So this is the notation for polynomials over the field f. Okay, and but I want to include only the ones which has degree exactly equals to n. Okay, so this is not a vector space. Why is that? Because that is not even a group. Well, the reason is simple. These guys, so x to the n plus 1 and minus x to the n plus 1, both are in Vn because both are polynomials of degree n. But if you add them up, then you get 2. And 2 is a constant. And since it's a constant, it cannot have degree n. So it is not part of Vn. So it fails to become a group with respect to plus. And that means it is not a group. And that means it cannot be a vector space because it violates the very basic setup of vector space. But if we are careful about how you handle this condition, we can make a vector space, a nice vector space structure out of it. We don't want just the polynomials with degree n, but we also want to include all the polynomials which has degree at most n. So the polynomials of degree n, n minus 1, and so on up to the constant ones. Okay, that will get rid of this problem that things can collapse into a smaller degree polynomial. Since you're including all the smaller degree polynomials, it will always be inside V of n. So if you improve your definition in some way, in this particular format that we are considering all the polynomials f with degrees at most n, then this will be a vector space over this particular field f. Okay. So this is how you can remedy some of the particular aspects which is preventing a particular set from being a vector space when the field is known. So this is one example, and it's by no means a constructive procedure. It depends on different kind of vector fields, and there is no one theory that will give you an idea on how to make a set into a vector space. Okay, this is the point of this exercise was not that. Now, let me also include other definition because this is needed in order for us to move forward. The vector space, 2 or 3 natural things for the vector space, at least the basic ideas, would be to define the linear independence, linear dependence, and spanning of a set. So it's time that we introduce those. So what do we mean by linear independence of a set? So when I say linear independence of a set, I mean linear independence of a set of vectors. So this is this S that, so we are going to denote this by some subset S of V. Now, say if this set S is finite, then linear independence just means that if you have some linear equation like this, and you equate that to 0, 0 being the vector 0, then it will have only one solution, and that solution is one solution in the set of scalars, and that solution is all of them have to be equal to 0. So if that happens for a finite set S containing the vectors v1 up to vn, then we say that S is linearly independent set or a linearly independent subset of the vector space V. Now, if this set S happens to be infinite, then the same thing would work, but now we are going to say that this equation will have solution only one unique solution, C1 up to Cn equals to 0 for any choice of vectors v1 through vn. So you can expect a vector space to have a subset which is linearly independent and which also has infinitely many vectors in it. So that is why I made the definition as broad as possible. So the second one would be the spanning. The idea of spanning is just that if you have a set S and we claim that it spans V, what we mean is that whatever vectors you have in the set S, you can always produce any element of your choice from your superset V by making a linear combination of elements from the vector vector subset S. If you can do that, then it says that spanning of V. So in other words, we generally write a spanning set like this. So say S is a set, then this is denoted by this angular brackets. What we mean is that we consider all the elements C1, V1 up to Cn, Vn, where Ci's are elements of F and Vi's are elements of S. So this is the set we are considering. And if this set happens to be equal to your vector space V, then we say that S spans V. So all the vectors can be represented in one of these ways. Okay, and if this set S happens to be both linearly independent and spanning, then this representation of a vector, of any vector in terms of linear combination of elements of S is unique in nature. If this is just a spanning set, then it doesn't have to be unique. But if it's both a spanning set and linear independent set, then it has to be unique. And in that case, S is called a basis of the vector space V. Okay, so it basically makes up all the elements of V. That's why it's called basis. And the dimension,
Sir,
the vector space dimension.
Sir, I have a small question, sir.
Mhm.
Every Li set have a cardinality finite, sir.
Well, for the definition, I wanted to make it as broad as possible. But for the rest of the lecture, you can take S to be finite. It won't interfere too much with it. But if it's infinite,
So, sir, the definition is the subset. Definition, Li set is a subset of a vector space. But do not.
Yes.
I know that, sir. If cardinality finite, like infinite, then how it express is not possible.
it is possible, but you only take finitely many elements at a time. You only take finitely many elements at a time. So say, for example, your set S is countably infinite. So we consider we have elements V1, V2 up to V1, V2, Vn up to infinitely many. And since it's countably many, I can do that. I can index them this way. And you can take any finite number of these guys as you want. You take a linear combination of this, and then move on to the next bunch of finitely many elements. Take a linear combination of that, and so on. Move on like that. So
Sir, any definition in geometrical form, sir? Li set represent in geometrical form.
Geometrical form. What do you mean by geometrical form?
Sir, how to represent in geometrical form, sir? The geometric.
Right now, there is no
Geometric in the
geometry. This is a
sense.
definition, right?
Okay, sir.
This is just a definition. Yeah, this is just a definition. The geometry, you have to take specific examples. Otherwise, this is too arbitrary to write in the geometrical form. So right now, all I'm saying that you have these two ideas of linearly independent set and spanning of a set. And if both of this happens together, we get a basis out of it. And the cardinality of S is called the dimension of the vector space V. And if this set happens to be finite, then the dimension of the vector space is finite. And if the cardinality of S is infinite, then the dimension of the vector space is also infinite. So there are infinite dimensional vector spaces, which might not show up in a first course in linear algebra, but you should know this, that there can be things like that. But in linear algebra, we can only make sense of finitely many elements. So that is why we define the spanning set of just collection of finitely many sums taken like one bunch at a time. Okay, so we are not trying to make sense of infinitely many things. Right. Now, the next idea is homomorphism. Well, like any categorical things, whenever you have two things, it is very natural for us to consider what kind of maps there can be between two of the sets that you have at your disposal. For if this V and W are just sets, then the functions are just set functions. Nothing else is required. But in our case, V and W are not just sets. These have some structure in it. So the way we define this function, it has to maintain the dignity of the structure. And that is why we want any function, or in this case, a homomorphism between two vector spaces V and W, to behave nicely. like this. So if you add up two vectors, v1 and v2, v1 and v2 being taken from big V, and then you apply phi to it, sorry, this is not phi, psi to it, then that is the same thing as applying psi to v1 and v2 first and then adding them up. And the same thing is, it behaves nicely with respect to the scalar multiplication. So these are something that we want a homomorphism to satisfy, and that is why we define the homomorphism to act that way. Now, this is the category. If you don't know about categories, then forget that I said that word. They're actually different kind of categories. So in this case, we have some special names for this homomorphism if it has some properties other than the ones that we have already defined. If it happens to be a homomorphism and it is also injective, then we will call it a monomorphism. And if it...
In definition 3, third line,
Yes.
from V is capital letter only, no, sir?
Capital, yes. Yes, this is capital V, yes.
Okay, sir, thank you.
Thank you. Right. And if this psi is a homomorphism and also happens to be surjective, meaning that it's onto, so when it's surjective, it means onto, and injective means one-to-one. If it's surjective, then we will call it an epimorphism. So homomorphism plus injective means monomorphism, and homomorphism plus onto means epimorphism. And if a homomorphism is such that it is both injective and surjective, then we call this an isomorphism. Okay? So that is the idea. An isomorphism is an invariant for vector spaces. Invariant is something which preserves the structure and also some other inherent properties of the vector space. In this case, by the inherent property, I mean that the basis will be taken to a basis. So if this psi happens to be an isomorphism, then a basis of V will be taken to a basis of W, and the dimension of V would exactly be the same as the dimension of W. So the dimension and the idea of basis would not change. So that is why I'm calling it an invariant. Now, of course, there are some...
Sir, can you explain, please, invariant once more?
Yes. So if the psi, this map psi, is an isomorphism, meaning that psi is a homomorphism, it is injective and it is surjective, then the dimension of V would be the same as dimension of W. And if you have a basis B of V, then this set of bases will be taken to a set of bases for W. So basis will go to a basis. That's what I mean by invariant. Of course, there are other properties that are satisfied, but I'm not going to go there. There are some interesting results, and these are by no means obvious, and it's in fact it's non-trivial, and it has taken few years for people to understand this properly, and but this is well known, and it has been well known for a long time. So you can pick up any book that you want in linear algebra, and you will get a proof of this, a proof of each of these guys actually, not just the A from theorem 1. Yeah, you will be able to, you should be able to make sense of the proof, because more or less the things are well defined and well understood now. So let me just state these things, because this will be useful in the problems, which is something that we are going to do next. after some examples. So the first thing is every vector space has a basis. Well, that is convenient. It's good to know that it has a basis. But the unfortunate thing is, if you see a proof of this particular fact, this is not something which is constructive. So the proof is not going to give you an idea on how to find a basis of the vector space. Maybe it will give you some ideas if the vector space is a finite dimensional vector space. But if it's not a finite dimensional vector space, then we use something called the Zorn's lemma in order to prove this, which is by no means constructive and it's quite axiomatic. So it's far from constructive as possible. But for the finite dimensional, what you do is you really look at a spanning set. So you start with picking one element, then you look at all the elements that you can reach out of that particular element that you have picked. So in other words, C times V. You look at you look at the set C times V, where you vary the C over the set of the field that you are considering, and now you pick up a new element which is not in the set that you just considered. Then this, let's say the one that you picked before is V, and the set and the element that you now picked, which is not part of the set, is W. Then V and W are going to be linearly independent. So now you put this W in and you construct a new set out of it, where this new set is the spanning of the vectors V and W. So you get a better set in the sense that there are more elements, and this is an improvement towards finding a basis. And you do this finitely many times because it's a finite dimensional vector space, and theoretically you're supposed to end this procedure after a certain time. So in this way, it can be constructed, but how you pick these elements, it's not intuitive at all. It depends on the vector space, and it doesn't have a specific algorithm that you can follow. This is as specific as it can get. Okay. Now, the linear independent set. If you consider all the linearly independent sets, then the maximum, or the maximal in this case, because some linearly independent set cannot be really compared by the subset idea. So that's why I'm using the maximal instead of maximum. The maximal linearly independent set of vector space V is going to be a basis of V. So linearly independent, it has to be maximum in order to be a basis, and the spanning set has to be minimal in order for it to be a basis. That's why it's kind of converging at a certain point when it is maximal linear and minimal spanning, and that is when you get the basis. If both of these satisfies, then of course you get a basis.
Sir, why you are using maximal instead of maximum?
Because there can be two sets which have both the same number of elements. For example, it doesn't have to be the same number of elements, but I'm just saying, for example, they have the same number of elements, but you cannot compare them. If you have two different sets which cannot be compared, but both of them are linearly independent, then you have to say maximal, because maximum is restricted when the collection that you are dealing with, it has a total order. For given any two elements, you can say that this is bigger and this is smaller for any two elements. But for here, you cannot do that. That's why I'm using maximal and minimal instead of maximum and minimum.
Okay, sir. Thank
Okay.
you.
All right. Now, very interesting thing is that if you consider a vector space V, and if you consider a subspace of it, now let's consider a basis of this subspace W. Then the nice thing about it is that you can maintain that basis, add some new elements to it, and you can get a basis for the bigger vector space, so the vector space V. So any basis for a subspace can be extended into a basis of the ambient space. Okay, so this is a very nice result, and we will be using that in one of the problems that we will see in a few minutes. Now, linear transform, okay, I might not have said that, but homomorphism is the same thing. So these are synonymous. Linear transformation and homomorphism, these are synonymous. So they are really the same thing. So I've written it here, but I don't think I said it. It's the same thing. So composition of two linear transformation is a linear transformation. Well, this is an easy fact, and you can prove it, obviously, but the other ones, it needs some work. It by no means is an obvious fact. Now, you can consider the set of all linear transformation once you have picked two vector spaces V and W. Say you have picked a vector space V, which has dimension m, and vector space W, which has dimension n. I'm really interested in the case where m and n are finite and non-zero. Okay, so that this doesn't become a trivial example. I don't want it to be a trivial example. So for this particular example, we are dealing with finite dimensional vector space V over the same field F. So the idea is that there is an intimate relation between defining a linear transformation and a matrix. So it is explained here. Say LVW is a set of all linear transformations from V to W. Then this is the same thing as telling you, well, it's the same being in, it has to be, I will explain it, what I mean by same. It's the same thing as defining or giving you the set of all matrices of order n by m. Note that this n and m has been switched. It's not m by n, it's n by m. It has been switched. Okay, now I should explain what I mean by same. What I mean by same is canonical, which is natural. As long as I tell you, or I tell you, or I announce at the beginning two bases of V and W. So if you're given a basis for V and a basis for W, then this is canonical. But if these bases are not given, then the canonical doesn't make sense. So that is why I have put the canonical under quotation. So this is how the construction works. Say you have some set B1, which is a basis of the vector space V, and B2, which is the basis of the vector space W. And you define a linear map T from B to W. Now, if you consider the image of the elements VIs, so T of V1, T of V2, T of Vn, and so on, these T of VIs, they're going to land in W. And since these T VIs are in W, we should be able to write this as a linear combination of elements of B2, because B2 is a basis, and hence, in particular, it is a spanning set. So that means for each I, we should be able to write it like this, where Aij's are scalars, and Wj's are, of course, these Wj's. And if now we get a matrix out of it, but the matrix A is defined by this guy right here. So A11, A12 to A1n, and then M1, A M2, A M M, and then you take the transpose of it to get this matrix. Okay, so this linear transformation gives rise to a matrix. Okay, and also if you're given a matrix, then you can define a T exactly by this relation, where this, as I said, this VIs and the WIs are announced. So if every matrix M will give rise to some linear transformation, but why is this well defined? First, you have to think about if you are going the other way, that if I tell you how the elements TVI looks like, does this mean that you can get the picture of the whole linear transformation? The answer is yes, because this VIs happens to be a basis. And if this is a basis, you can get all the elements of the vector space V out of these guys. And this representation is going to be unique. So as long as you have ideas about where the basis has been taken, you will get a uniquely defined linear transformation. So the reverse direction also works exactly we want it to. So that is why you have an isomorphism between the set of all linear transformation from V to W and the set of all matrices of order n cross m, where of course this m and m have been previously defined. So from now on, you can think of every matrix as being some linear transformation, and the governing equation is going to be this right here. Okay. Moving on, there are certain advantages if you are considering linear endomorphisms. Okay, let me define that term, linear endomorphism. We have defined epimorphism. We have defined monomorphism. What is an endomorphism? Endomorphism is when the domain and the codomain vector spaces happen to be the same. Okay, that is what that is what is known as endomorphism. So if you have some linear transformation that goes from V to V, and this V happens to be a finite dimensional vector space, then it is injective even only if it is surjective. Okay, and it is in fact true in the general case of modules, free modules, but we don't have to go there in case you don't know it. You just have to know that if you want to check if T is injective and it happens to be an endomorphism, and also it happens to be a finite dimensional vector space, then say for some reason you are stuck, you cannot prove for some reason that it is injective, then you can try proving that it is surjective. If you are successful in doing that, then it would also imply that it is injective. So it is injective if and only if it is surjective, as long as this linear transformation is an endomorphism and it is finite dimension. All right. And finally, I would like to say that the finite dimensional, when you have a fixed field, then you have exactly one up to isomorphism vector space of dimension n. And that vector space is f to the n. So in other words, if it's finite dimensional, then every vector space V, which is a vector space of dimension n over f, is going to be isomorphic to f to the n, where f to the n is the Cartesian product of f with itself n times. Okay, so the finite dimensional vector spaces, to some extent, are easier to deal with than infinite dimensional vector space. Now, let me give some examples which also can be treated as problems. I would like to ask a question to Dr. Vinod. Do you want to take a break or should we continue?
Continue, sir.
Yeah, we can continue.
Okay. Remember that we defined this vector space F, a script F, which is a vector space containing all the functions that goes from X to R. And let's try to think of what would be a linearly independent subset of this vector space. Now, say for each small x in capital X, we define a function chi sub x of y to be equals to 1 when x and y are the same, and 0 otherwise. Okay? So this is going to be a linearly independent subset of script f of x. And it's actually kind of easy to see, but this is not going to be a spanning set unless X is itself a finite set. Well, why is that? Well, why is finite set enough? Because, say, if you have let me give you an example of this particular example. So say, if you have a function, say, okay, maybe define X to be A, B, C, and you have a function F, which takes A to maybe 2, F of B to 5, and F of C to 10. Okay, then you can represent F of F of X as 2 chi A X plus 5 chi B X plus 10 chi C X. Okay, and then by the definition you can check that if of A is going to go to 2, if of B is going to go to 5, and if of C is going to go to 10. So you can hit exactly the elements that you want to, as long as X is finite. And since it's finite, you can write this as a sum, because finite sums make sense. So that is why it will also be a spanning set, provided that X is finite. But if X is infinite, then the only way that this can be a spanning set is to write it as an infinite sum, but infinite sum doesn't make sense in R, so that's why we fail. That's why it won't be spanning. Okay? Any question?
Sir, can you provide this PDF?
Can I provide what?
This PDF file, sir.
Yeah, sure. I will share it with the group or to Dr. Vinod, if whatever is needed. I can do that. Yes.
In chat box, can you provide, sir? It's not able to post.
Right now, I don't think I can do that because I'm still writing on this.
Yes, Sayak, we can provide it with the recording of this session.
Okay, yeah, I will, after I'm done with all of these writings and everything, I will share it with Dr. Vinod, and Dr. Vinod, I'm sure he will share it with you.
Okay, sir. Thank you. Okay.
We can also talk about the vector space C over R. And we can consider this linear transformation where some element Z is taken to its conjugate. So when I say conjugate, I really mean that this linear transformation, this particular one that we have chosen, is taking A plus BI to A minus BI. That's what I mean by conjugate. So if this guy is A plus BI, then Z bar means A minus BI. Okay, so this is in fact an isomorphism. And that is a very easy fact to check. Okay, it's an isomorphism. And the associated matrix, we remember that we have talked about this matrix thing, that all the transformation is representable in terms of a matrix. And how can you do that in this particular case? Well, I didn't exactly give a name to this. Let's call this the map psi for now. Or okay, maybe I was saying T. So let's stick with that, T. This map is T. So what is T of 1? T of 1 is 1, right? Because 1 can be written as A plus 0 times I. So it's just 1. And T of I, by the way, we are talking about the transformation under this basis, 1, comma I. So this is going to be minus I. So I can write 1 as 1 plus 0 times I, and this as 0 plus minus 1 times I. So the matrix, we can write this as, so 1 is going to be here, and then 0 should be written here, and then 0 goes here, and minus 1 goes here. So this is the corresponding matrix. Okay? And in fact, this vector space C over R is a finite dimension, and as I mentioned, this is a basis. So this is a two-dimensional vector space. Dimension 2 vector space. Dimension 2 R vector space, to be more precise.
Sir, can you give example for other bases, sir, except 1, I? Can you give example?
You can have another example, say 1, minus I. That also works as a basis.
Sir,
So if
1, I, except other than that, what you can define, sir? Except I, 1, except 1, I or 1, minus I. Can you use other numbers, sir? With that basis, you can define matrix.
Yes, you can have bases like, say, for example, 1, this. That also works. Okay, this is also a basis. And
Can you convert to matrix, sir?
yes. So let's try that. I have to, let me see if I can add a page. Yes, let me just add a page here so that I don't have to remove anything. Okay.
Excuse me, Sayak. Actually, you can leave that as an exercise for them. You can just give hints how to do that.
Okay. So what you have to do really is basically look at T of 1, which and then T of 1 plus I. So T of 1 is 1, and this is going to be that. And then the matrix is easy. You just write it in terms of, so this is just that, and this is just 1 plus minus 1I. So the matrix is now 1, 0, and 0 minus 1. Okay. So, no, sorry, 1, 0, and 1 minus 1, sorry. 1, 0, and 1 minus 1. So that's going to be your matrix. So you always target the basis that you're considering, look at the element where it is going, and then represent that in terms of the basis that you have of the codomain. And after that, once you do the representation in terms of the basis of the codomain, you should be able to get the AIJs. And these AIJs are going to give you the elements of the matrix that you consider. Okay.
Thank you, sir. Thank you, sir.
Yeah. Right. Now remember that we defined the vector space V sub n in example 5, which was the set of all polynomials of degree at most n. Yeah, it's a set of all polynomials of degree at most n. This is also a finite dimensional vector space, and the dimension is n plus 1, where a very nice basis is this. Of course, there can be other bases, but this is the one that people consider, and people are happy with it. Okay, unless you have some different problems in mind. Okay, let me just take a 1 minute break. I just have to do something. I will be right back. Okay. Is that okay, Dr. Vinod?
Sorry?
Let me just take a 1 minute break. I just have to do something. I will be back in 1 minute.
Okay.
Is that okay?
Okay. Sure.
Okay. Thank you. Okay. There are some other examples also. Since we have talked about the possibility of vector spaces having infinite dimension, so it's only fair that I give you an example of one at least. So this Q vector space R, meaning that R is a vector space over Q, if you consider this particular vector space with the obvious operations, in this case, the Q is the field, and R, we are just considering the plus operation of R. Okay. Then this is an infinite dimensional vector space. All right. Now, how do you prove that it is infinite dimensional? Remember that in theorem 1, one of those several parts I've mentioned, then the maximal linearly independent set is going to be a basis. So if I can produce an example of a subset of R which has infinitely many elements and which is also linearly independent, then it will follow from the statement that I mentioned that the vector space R over Q will be infinite dimensional, because if there is at least one in a collection of infinitely many elements which is linearly independent, then there is a possibility of building it up. You cannot go down really if you want to reach a basis. So that is how that is one way of proving that a vector space is infinite dimensional. So that is what we are going to prove. So we are going to define a set S, which is the set of logarithms of primes. A logarithm of primes, a log of p. So when I say log, I actually mean natural log. Okay. And this is an infinite set. Well, why? Because the number of primes is infinite, as you all know, and log is a strictly increasing function. So none of the value in this set will be repeated, and hence it is an infinite set. Okay, so now that we have convinced ourselves that S is infinite, let's see why S is linearly independent. Remember that when dealing with infinite set, we in order to prove linear independence, we can pick any collection that we want, and we want to show that by picking this collection, it will be linearly independent. So that is exactly what we do. We pick n primes, n being some positive integer, p1 through pn, and also suppose that they are rational numbers c1 through cn, such that this equality holds. And if I can show that these ci guys are equals to 0, then we should be done. That would prove that S is linearly independent. Now, how would we do that? Well, first of all, you see that these CIs, what are these CIs? These CIs are rational numbers. So each and every CI comes with the numerator and the denominator. And these numerators and denominators are nothing but integers. So you can multiply both the sides of equality 1 by the LCM of the denominators of the CIs. And after multiplying that, all the coefficients are just integers. Okay? So without much abuse of notation, I'm going to do that. I'm going to multiply this equation by the LCM so that the CIs, which are now new CIs, not the old ones, not necessarily the old ones, I mean, is integers, are integers. Okay? So we make this small change without loss of generality, and we now assume that CIs are integers. Okay, but how does that help? Well, now you can use you can take exponential function on both sides. If we do that, then exponential turns log into products. So the left-hand side just becomes p to the ci, and the right-hand side is just e to the 0, which is just 1. But these pi are prime numbers. So in particular, this is greater than 1, strictly greater than 1. And ci's are integers. So the only way that the product of some primes, it doesn't have to be, the ci's doesn't have to be positive. It can be negative as well. So some primes upstairs, some prime downstairs, like that. And these PIs are distinct. They are not any of the same, so that things can cancel out. It's not like that. All the PIs that you have picked are different. So there is no cancellation between numerators and denominators. The only way this can happen is that all the CIs that you're considering are individually zeros. And that is exactly what we wanted to prove. Since the CIs are zeros, S is linearly independent. Something fun would be to try to prove that S is not a spanning set. In other words, you cannot get all the elements of R by just making linear combinations out of the elements of S. You should try to prove it. Okay, that would be a very fun exercise. Now I think it's better to move on to
Q is field, R is vector space. Am I right?
Yes, R plus is the vector space. So I'm not really using the dot operation or the product operation of R. It's just R plus.
Okay, sir. Okay. Why you didn't mention there, sir?
Oh, I did. I'm just talking about the group structure, the additive group structure of R, not dot.
Okay. Okay, sir.
Yeah. Because if I was considering the multiplicative structure, then I remember that with the multiplicative structure, R is not a group. You have to get rid of 0 in order to make it a group. So the only way that this can become a vector space is we talk about R plus, not R dot.
Okay, sir. Okay, sir.
Okay, so the first problem is, I took it from GATE, which was shared by Dr. Vinod. Now, we have covered all the bases for this problem, so we can just get on with it. Say you have this linear transformation, which is going from R3 to R3. So this is an endomorphism on R3. you have defined this T on the basis. So you can actually see that this vector is 1, 0, 0, and then 1, 1, 0, and 1, 1, 1. This is a basis. Well, you can of course do it the rigorous way, or you can just prove that this is linearly independent. And since this is linearly independent, and the basis of R3 over R. So when I say, okay, so that has to be as said, that when I say R3, I mean the vector space R3 over R. Okay, not over Q or anything, over R. So this R3 vector space is dimension 3. And we now have a linearly independent subset of R3, which contains 3 elements. So this is the right number, and it is linearly independent. That means it must be a basis. And as we talked about before, defining a linear transformation on just the basis element is good enough. That gives the whole T over R3. Now we want to investigate if T is one-to-one or onto or not. Okay, but you see this R3 over R, this is a finite dimensional vector space. So either it is both one-to-one or onto, or it is neither. So it either B is true or C is true. A and B, right off the bat, you can cancel them. All right. Okay. So I'm just going to see if this is one-to-one or not. Well, we can look at the images, which is 0, 1, 1, 1, 0, 1, and 1, 1, 2. Okay. This is not linearly independent. Why is that? One very nice way, in fact, to check if a collection of the vectors like this is linearly independent or not is to, for endomorphism actually, if it's not an endomorphism, it might not work. If it is endomorphism, it will work because we will have a square matrix and the determinant will make sense. So if you calculate this determinant, you will get 0. So I'm taking it for granted that you know how to find the value of the determinant of a given matrix. So since this is 0, that means that these guys are linearly dependent. And linearly dependent means it cannot be a basis. So a basis will not go to a basis. The basis is not taken by T to a basis. That means T cannot be an isomorphism, or in fact, in this case, it fails to be an onto, and hence it cannot be an isomorphism. Okay. So this is the first problem that we have seen. The next problem actually talks about something called diagonalization, which is a very important thing in linear algebra. And I didn't exactly have a lot of time to look at the gate problems, but I have seen enough to know that it turns up quite a while, these kind of problems. So that is why I picked it. So let's define eigenvalue and eigenvectors. So eigenvalue is, so say that you have a given matrix A, and we will say that lambda is an eigenvalue of V if there exists some non-zero vector V such that A times V is going to be the same as lambda of V. Okay, if something like that happens for a non-zero vector V, then lambda is said to be an eigenvalue of the vectors of the matrix A. Now, what exactly does this entail? That is exactly how you get the characteristic equation of a matrix, because if this AV equals to lambda V holds, then it means, so this is the same thing as saying that a V minus lambda, say, okay, I didn't write the order of the matrix. So this is a matrix, which is a square matrix. Yes, so I should say square matrix, not just a matrix of order n. So In lambda V is a zero matrix. Now you can take V as a common factor, because this is just a column vector. So when I say non-zero vector, I mean a column vector actually of dimension 1 by n. And then you get something like this. So what V does is it exactly takes a linear combination of the columns of the matrix A minus lambda In. So what we are saying really is that the columns of the matrix A minus lambda In, it is not linearly independent, because some combination is giving you a zero vector. And if that is true, that just means that the determinant of this guy is equals to zero. If the we have just seen this in the last problem, that if the columns or the rows of a matrix is not linearly independent, then the determinant has to be equals to zero. So this is what is known as the characteristic equation. So this is characteristic equation of A. And we have the celebrated theorem by Cayley-Hamilton that every matrix A satisfies its characteristic equation. Okay. Right. So in other words, this will be A minus lambda In. Rather, the determinant of this matrix is zero. Because A actually comes with elements. So when you write it out, then it will be just a polynomial in lambda. Okay, so this is just a polynomial in lambda. Now you can make the same type of idea when you move from a matrix, from a square matrix to an endomorphism from V to V, and then you can define it the same way. Okay, so I'm going to skip that because I'll be providing you the PDF file. You can take a look at it. And we are a little pressed for time, so I'm going to skip that. We have the, for each lambda, eigenvalue lambda, we will have an eigenspace, which is really the set of all vectors that satisfies this. So V sub lambda will be the eigenspace associated to an eigenvalue lambda. Now, say that your characteristic equation, it looks like something like maybe lambda minus 1 cubed, and then lambda minus 3 squared, and then lambda minus, I don't know, 5 maybe. So 1 is a eigenvalue of whatever the matrix is coming from. It doesn't matter for the moment. So 1 is a eigenvalue of a matrix of multiplicity 3, because it repeats 3 times. And this multiplicity, we will call this algebraic multiplicity of corresponding to lambda. Okay, and there's also a concept of geometric multiplicity. The geometric multiplicity would be corresponding to this one, we should be able to make an eigenspace V1 And the dimension of that eigenspace will be the geometric multiplicity corresponding to 1. It is a well-known fact that when eigenvalue is fixed, eigenvalue lambda is fixed, then the algebraic multiplicity will always be at least as much as the geometric multiplicity. And if the geometric multiplicity and the algebraic multiplicity happens to be the same for all the eigenvalues of a given matrix A, then we will say that A is diagonalizable. But that is a consequence rather than a definition. So let me define this diagonalizable idea. We say that a square matrix of order n is diagonalizable if you can find a non-singular matrix S of order n such that when you do this S inverse AS, because it's non-singular, the inverse of the matrix S exists, and that's what S inverse means. S inverse AS will give you a diagonal matrix. Okay, so that is the idea of diagonalizable. But you see, this definition, it doesn't help. Why it doesn't help? Because it doesn't give you, suppose you find some way to check that it is diagonalizable. For example, you can, find all the eigenvalues, and you can check that for all the eigenvalues, the algebraic multiplicity is equal to the geometric multiplicity. Then, as I mentioned, it is diagonalizable. Okay, so you know that it's diagonalizable, but how to find this matrix S? So this matrix S is not mysterious at all. This matrix S is basically the set of all the vectors in the eigenspace. Okay, I will give you an example in a moment. So say for lambda 1, I'm giving you one example. This is not always going to be the case. Say for one example, you have n distinct eigenvalues. So eigenvalues doesn't repeat. Say for this one, lambda 1 and up to lambda n, and this lambda i's are distinct. So that means that the algebraic multiplicity associated to each of the lambda i's is 1, and the geometric multiplicity, of course, the eigenspace cannot have dimension less than 1, and it cannot be more than 1, so it has to be exactly equal to 1. So in this case, it is diagonalizable. So since it's a dimension 1, you just pick some vector, eigenvector of lambda 1, and similarly an eigenvector for lambda n. Okay, and what I'm telling you is you construct this S in this format. So in the first column, you write x1. In the second column, you write x2. And in the last column, you write xn. If you define S that way, then S inverse AS is going to give you a diagonal matrix, but not just any diagonal matrix. Is going to give you the diagonal matrix where the diagonal is occupied by the eigenvectors itself, and the other ones are just 0. So this is not mysterious at all. When it is diagonalizable, S is just the collection of the set of linearly independent eigenvectors. And by the definition, we have made sure, because the geometric multiplicity is the same thing as, it is the same as algebraic multiplicity for a diagonalizable matrix, then we have enough linearly independent eigenvectors to construct this S, and that's how you can do it. Okay, so the construction of S is easy as long as you do this computation. But this is a specific case. I've here assumed that lambda i's are different from lambda j's as long as the indexes are not the same. But you can, since the algebraic multiplicity is the same as geometric multiplicity, you can take some of the lambda i's to be the same. So you write them like, say, lambda 1, lambda 2, and lambda 3 are the same. Then lambda 4 is different than the others. And then lambda 5 and lambda 6 are the same. Then you write it like that. Since then you will get enough number of linearly independent eigenvectors to construct the matrix S. And then you do S inverse AS to get that. Where the ordering would also appear in exactly this way, the way you're considering the columns. So if you write x1 first, then you get lambda 1 first. If you take x2 first, then you get lambda 2 as a second element, and so on. Okay, so it's surprisingly well behaved. Some remarks are necessary in order to move on to the next problem. Not all matrices are diagonalizable. Okay, so this is definitely, in other words, diagonalizable matrices are definitely special matrices. Also, the diagonalizable thing is not well behaved under products. So in other words, what I mean by that is, if you have two diagonalizable matrices, A and B, even if they are of the same order, then a product of A and B might not be diagonalizable. Okay, 3 and 4 I've kind of explained before. And 5 is something interesting because 5 is like a follow-up of 2, I would say, that when would be a product of two diagonalizable matrices be a diagonalizable matrix? So this is giving you a condition. Let's say A and B are two diagonalizable matrices of the same order, say n, for example, then AB is going to be diagonalizable if and only if AB is equal to BA. In other words, A and B commutes on the product. And that is the same thing as saying that A and B share the same eigenvector matrix S. That is actually very easy to see, the last point at least, which is if this happens, then you will have S inverse S equals to, say, D, so which is D, well, let's say D1, where D is a diagonal matrix, and S inverse BS, because they share the same eigenvector matrix, I can still use the same S, say D2, then AB S inverse AS, which is really equals to S inverse AS times S inverse BS. And since the matrix multiplication is associative, they are really the same. You can rearrange the stuffs, rearrange the brackets, the multiplication would still make sense. And then which is just D1 times D2, which is of course a diagonal matrix. Okay, so that's how it works. These are something very important when you are solving problems like when to understand if something is diagonalizable or not. Okay, so let's consider this matrix M equals to 4 minus 3, 1, 0, which is a 2 by 2 matrix. And consider the statements P and Q given in this way. The P is M to the 8 plus M to the 12 is diagonalizable. And Q says that M to the 7 plus M to the 9 is diagonalizable. You have to say if either P or Q is true or not. Okay, so how would you do that? First of all, I would leave it as an exercise for you to check that M is diagonalizable matrix. In this case, it's easy to check because the values of M are distinct. There are two distinct eigenvalues of M. And I have already mentioned that when you have distinct eigenvalues, then it's always diagonalizable. Okay. So in this case, it's easy. But these are higher powers. And you know that in order to calculate this in the exam, and after that, you have to do all the calculations of eigenvectors and eigenspace and so on. It will take a lot of time. It's not worth it that much. So what do? We just use the ideas that the remark mentioned. I'm going to write m to the 8 as m to the 4 plus I4, where I4, it means the identity matrix of order 4. And I'm going to write M7 as M7 plus M to the 9 as I4 plus M squared. Now, as I mentioned, M is a diagonalizable matrix. And since M commutes with itself, obviously, that means by this remark 5, M squared, M cubed, M to the 4, and so on, all the powers of M really are also diagonalizable. Okay, so in particular, this one right here and this one, both are diagonalizable. And you do have to check these two guys as well. M to the 4 plus I4, it shouldn't take too much time. You can calculate that to be equals to 122 minus 120 and 40 minus 38. You can look at the characteristic equation and you can find that the eigenvalues are 2 and 82. So the eigenvalues are distinct. That means m to the 4 plus I4 is a diagonalizable matrix. And we do the same thing for the other one, m squared plus I4. This is even easier to calculate, which will be this matrix. And you can check that the eigenvalues are 2 and 10. Okay, so here also you have distinct eigenvalues, 2 and 10. That means m squared plus I4 is also diagonalizable. Now, what have we concluded from all of this computation? We've concluded that this one is diagonalizable and so is this. And since these two matrices commute, we have by remark 5 in the previous page that the product must also be a diagonalizable matrix. Okay, and same thing goes for this one. They also commute. So that is also diagonalizable. So you pick C.
Excuse me, sir. Here we found out that m raised to 8 and m raised to 7, they will be diagonalizable. But then how did we verify that the product m raised to 8 and m raised to 4 plus I4, they commute? How did we verify that?
Oh, because you see, I did not actually verify that, but it's not hard to do that. M to the 8, and what is the other one? M to the 4 plus I4. If you write it this way, then it's m to the 8 times m to the 4 plus m to the 8 times I4, which is just m to the 12 plus m to the 8, right? And then if you do this the other way, eight, by the way, it's going to be m to the 4 dot m to the 8 plus I4 times m to the 8, which will also be the same. So it is indeed commutative, commutes. These two matrices commute. Because it only involves M and I, so it must commute. There is no other matrix. I4 is in the center of this matrix group. So it commutes with everything.
Yes, sir. Thank you.
Mhm. Okay. So maybe let me choose this one and this one. Let me try to do both of these. The other ones are, if you want, I can share the solution with solution with you another time or some other time. I'm not sure what to do about that. But since we are a little bit pressed for time, I would like to move on to other type of problems. For example, let me do this one first. Say you have a matrix A, and the elements are taken from the complex numbers. So this A is from this set, M3C, where M3C is the set of all matrices of order 3, where the elements are taken from the set of complex numbers. Now, how would you find the trace of this guy? Well, first of all, we have to find what is the trace of, actually, actually, you don't have to find the trace of A first. What we have to find is we have to find the eigenvalues. So what are the eigenvalues of A? And that also requires some calculation, but you should be able to check that the eigenvalues are really lambda equals 1, omega, and omega squared. Well, what are this omega and omega squared? These are the primitive roots of unity. So for example, you can take omega to be equals to -1 plus √3 over I over 2, and then omega squared is going to be -1 minus √3 over I, √3 times I over 2. Okay, so if you do that, then there are some properties that this omega satisfied. Of course, this is a primitive third root of unity. Omega cubed is going to be 1, and also omega squared plus omega plus 1 is going to be equals to 0. Okay. Now, what trace of A to the 1 or 2 is trace of a matrix, a square matrix A, or maybe, sorry, it's A to the 1 or 2. A to the 1 or 2 is just the numbers 1 to the 1 or 2, where 1 is the first eigenvalue, omega to the 1 or 2, and then omega squared to the 1 or 2. So in general, trace of some matrix, so say fact, this is the fact that A is a square matrix of order n with eigenvectors, eigenvalues, lambda 1 up to lambda n, not necessarily distinct. Then A to the m, where m is some positive integer, the trace of that is going to be equals to lambda 1 to the m up to lambda n to the m. So this is a nice fact. And you can see that this is definitely true when m is equals to 1, because trace of A is just the sum of all the eigenvalues. Okay, which comes from really the characteristic equation. Anyway, so let's get back to our question. What is this? 1 to the 102 is obviously 1. W to the 102 is, well, because of this condition, I can write, let's see. So 102 is a multiple of 3. So I can do this. So it's going to be 3 and then something. So whatever. So the 102 is equals to, let's say, 3 times x, whatever that x is, you can calculate easily. So this, and then this is going to be that. And since this one is equals to 1, this one is equals to 1, then the power is also going to be equals to 1. So the trace gives you 3. Okay. All right, so there were other problems, but in order to get the basics down, I had to spend some time on the examples. Hopefully the examples helped. And now I'm really out of time, so I think it's good to stop at this point. All
Okay,
right.
thank you. Yeah, yes, right. Thank you, Sayak, for this nice session on basic linear algebra and some selected problems from that area. Dear participants, now it is a time for feedback. You can share the feedback and also you can ask your queries. Yes, Rose.
So good evening, everyone. Today's session was interactive and more interesting as we get to know about the basics of linear algebra. Thank you, Sayak sir, for conducting the session, and thank you, Vinod sir, for organizing the session. Thank you.
Thank you.
Thank you, Rose. Others?
Good evening, sir.
Hi.
Yes.
Sir, my name is 𝗟𝗶𝘁𝗵. I'm from St. Thomas College, Tirur. I'm a final year BSc student. It was really informative. Actually, you started from the basics. I found that really interesting because although I have studied linear algebra, it was like the start of the session was like a revision for me, and I was able to follow the whole session. Thank you, sir, for the session. Thank you, Vinod, sir, for organizing the session.
Thank you.
Thank you, Gopika.
Hello, sir.
Yeah, it's Praveen.
Hello.
Sir, my name is Praveen. I am from St. Thomas College, Thrissur. I really loved the problem solving session. Each of the steps you explained it. Each of the steps you explained it very thoroughly, and why did it commute and all those steps were dealt in detail. So it has helped me to build a strong base for linear algebra. So expecting more sessions from you. Thank you.
Thank you, Praveen.
So good evening, everyone. Myself Isha. Sayak sir, the session was really nice. Yeah, as Praveen said, you covered all basic things, and I expect more problem solving session from you because that was really nice. And thank you, Vinod sir, for organizing this.
Thank you, Isha. Any others? Yeah, dear participants, if any of you would like to ask, yeah, Ms. Akhila.
Sir,
Yes, we.
myself Aglaji Suresh. I'm from St. Teresa's College, Ernakulam. First of all, thank you, Sayak sir, for this session. It was really interesting, and I like the problem solving session. And also, thank you, Vinod sir, for organizing this class. Thank you.
Thank you, Akhila.
Hi, sir. Good evening.
Yes.
Hello.
Sir, at the beginning of the session, you told that you refer to some Indian author book which explains linear algebra and a geometrical approach. Could you please repeat that book?
Yeah, sure. Okay, so this book I used in my undergrad and it helped me. I don't use it much right now, but it's pretty good.
Okay.
Yeah, that is a book by Kumaresan sir.
Okay.
Yeah,
you.
it's
Professor
pretty
S.
decent.
Kumaresan.
It's very decent, yes. I mean, it skips some topics, but the main idea of this book was to use linear algebra for geometrical purposes, and that purpose has been served very nicely. I think it's very nicely done. So,
Right. Thank you.
Okay, I think there is no further queries or feedbacks from others. So thank you, Sayak, for this nice session, and hope that we can arrange more sessions by you in future.
okay, thank you. Thank you for inviting me.
Yeah. Okay, let us wind up here. Thank you.
Okay. Bye.
Someone is asking for the PDF. Please do share it with me. We can share it to
Yes,
the
of course.
students.
Yeah, I will share the PDF with all the notes that I've written. That would be easier.
Yeah, you can also include some hints for that problems. That will be helpful for them, if possible.
Yeah, it's possible, but I cannot probably do that right now. But maybe sometime tomorrow. Is that okay?
Yeah, after 1 or 2 days is enough, I think. If possible,
Okay.
we will do the record. We will do the recording by that time. If it's possible, we can share it with that.
Okay, perfect. Thank you.
Okay, thank you everyone. Let's wind up here.
Bye.